Okay, so today we started off with the ester hydrolysis reaction, and the ester hydrolysis reaction is basically when you combine an ethanoate, that means an ester, with sodium hydroxide, and in that process you get sodium ethanoate here and the propanol. Now, hydrolysis means cutting with the help of water. So, hydrolysis basically means cutting in the presence of water. So you've actually broken the propyl ethanoate molecule with the help of water. And so do not get the wrong idea. The NaOH basically is just there to attach itself to the broken up ethanoate molecule. The water actually will break this molecule up right about here. So what water does is it will break the molecule up to give you CH3, C double bond O negative, plus CH2, CH2, CH3, and the Na and OH, basically the Na just attaches itself here. When you break it up with water, the OH group actually attaches itself to the broken up molecule on the right. So water does the job of breaking this up, and water just does the job of initially forming the alcohol, and then Na just attaches onto it. It latches onto it. Although in the book your final reaction is given, so just remember that it is actually because of water that you get the broken up molecule in the first place, and the Na positive just latches onto it. Um, Hydrolysis means cutting in the presence of water, or breaking up breaking up a molecule in the presence of water, breaking up an ester using water. Now, where did the water come from? If it's not clear, it is actually from the NaOH. It's an aqueous solution. NaOH is highly diluted for this reaction to occur. If you use highly concentrated, this reaction wouldn't occur. Okay, so now that you have understood what hydrolysis is, which is just breaking up in the presence of water, uh, we need to move on to the next bit, which is completing the following hydrolysis reactions. So I've written below a reaction between animal fat and 3NaOH, that means sodium hydroxide, and I'm expecting you to come up with the final product. So have a go at it, and then we'll discuss. So this reaction is similar to the reaction that we did previously, in which we started with an ester and we hydrolyzed it with the help of dilute NaOH to give sodium ethanoate and propanol. In this case, because we are using a bigger molecule, we are using animal fat. We are getting a triol, which is propene 1,2,3 triol, uh, which is also known as glycerol. Propane 1,2,3 triol, which is glycerol. And the second part that we get is called sodium stearate, commonly known as soap. That is actually how we make soap in the first place. So now the next question that I have is, what is saponification? Well, this process in which we take an animal fat and combine it with a strong base, a caustic base, like NaOH. The process of making soap or sodium stearate from animal fat using a strong base is called saponification. Saponification is just the process of soap making. So the process of making soap of making soap by starting off with animal fat and combining it with with a strong base. Process of making soap by starting off with animal fat and combining with a strong base like NaOH is called NaOH is saponification. Now, saponification doesn't necessarily have to be with a base like NaOH. It could be with a base like lithium hydroxide. And if you use lithium hydroxide, the only difference would be that the soap would be harder compared to the soap that you'd get with sodium hydroxide. And if you do the process with potassium hydroxide, the soap would be softer. Now, with that, you should be able to attempt set 18, question number 8. Once you've done that, we'll go on to the last part of the chapter. Thanks. Okay, one last question to go, and then we are done with this chapter. We're talking about the cleaning action of soaps and detergents. So below is a typical soap molecule. Now that's a typical soap molecule, and I'm exposing this to hamburger grease stain. Uh, oh, I forgot to draw it, but I'll quickly do that. So I'm gonna expose it to hamburger grease stain. So let's say this is the fabric, and there's a grease stain on it from eating a hamburger, whatever. Now, what I'm asking you to do is show me how uh, you would be able to remove the hamburger grease stain with the help of this molecule. So think of a mechanism in which, and think of a way, think of the possibilities that this single molecule can remove this spherical uh, grease stain from this fabric that you highly desire. So give it a chance. Give it a go. Okay, a quick hint on how to go about this is that this part of the molecule is called the hydro hydro hydrophobic side. Now, what does phobia mean? Scared. This side is actually scared of the water. This side is called this particular group is the hydrophilic group. What does phil mean? A philanthropist. Love. So phil means love. So this is the water loving side. Now, when you expose this to the grease, the hamburger grease, the water hating side would go and attach itself on the grease molecule. So the water heating side will attach itself here, leaving the water loving side exposed to the red bit. So the water loving side would actually be exposed to the water because it has no problems with the water. Now that obviously that's not just the only molecule. There would be a number of molecules which will attach itself here. That's another molecule, and there'll be thousands of molecules which will attach itself. And once they do attach themselves from all sides, then they have uh, enough contact to remove the spherical globule of grease from your fabric. So that's how it works. So once you've understood this, I have another question. How would you show with a chemical equation why soaps are ineffective in hard water? Now, if you're wondering what hard water is water which has calcium or magnesium ions in it. So a high concentration of calcium ions and magnesium ions in it. So how would you show that why are soaps ineffective in hard water but they're fine when you use normal tap water, soap water, soft water? So try this one out as well. Now, a chemical equation that would show that is, and once I've written down the chemical equation, I will explain why that's the case, why it becomes insoluble. CH3, CH2, 16, COO negative. And if it was so in the case of hard water where you have calcium 2 positive ions, the salt that we get, the calcium salt that we get, is itself insoluble in water. Since it is insoluble in water, that renders the soap ineffective. So, insoluble salt renders soap ineffective. Insoluble salt renders insoluble salt renders soap ineffective. Renders soap ineffective. Okay. One last question, and I might just leave this for homework. So, unlike soaps, detergents work very well in hard water. With the help of a diagram of a typical detergent molecule, could you explain why this is the case? So, why do detergents work in hard water, uh, and why don't soaps? We know why soaps don't work. Why do detergents end up working in hard water? So just have a go through this, and we will discuss this at the start of the lesson tomorrow. And with that, we are done with the whole chapter. Set 18 is your homework. You can leave the questions on detergents for now. We'll discuss detergents tomorrow. But other than that, you should be comfortable in set 18. Tomorrow we start empirical formula, and that should be the chapter that we finish off before the end of this term, and then we just have two left. Thanks.